So that's it. So unfortunately, Jorge is not here to host the meeting because normally he gives the presentation. So I'll do that in his stead. Jorge is having some problems with the internet. So it's a great pleasure to have with us Jonathan Duchov for the last seminar to close this seminar series on COVID-19. So Jonathan Duchov, he's a very well-known researcher working in epidemiology. So actually he's a theoretical biologist with a broad interest in computational and statistical approaches to practical biological questions with a particular interest in dynamical questions. For instance, how systems are shaped at large scales by the way that they change at the smaller scales. And his current research is mostly focused on infectious diseases of humans. He has a very impressive track record of publications. He has more than 12,000 citations, okay, and he has been very, very active working on COVID. 12,000. What did I say? So he has been working very, very, very intensely on COVID-19. So that's why we invited him. So Jonathan, thank you very much for being with us. So we are all yours. So I will ask everybody to switch off microphones and also cameras. Thank you. Go ahead, Jonathan.
Thank you very much. Thank you for the invitation and thank you for that kind introduction. And these should be my slides. I'm going, oh, sorry. Google has changed its thing and I failed to delete all of my notifications. I hope that's not going to be a problem and I hope you don't see them. So I'm assuming you see my slides or that you'll tell me if you don't.
Yeah, we see them. Go ahead.
So I'm going to talk to you about time distributions in coronavirus control. I left out some of the introductory slides about dynamical modeling because I know that this is the end of a series. And I think that you've seen a lot of this, but I do want to talk a little bit about my view of dynamical modeling, which is that it's a critical tool because it's what we use to connect scales, in this case, between continental level patterns of the spread of measles and individual events by which measles are spread. And a dynamical model is the only way to link these two, and it's the way we link in both directions. We use large scale data to try to infer what people are doing, and we also ask if we can change what people are doing, how might that come back and affect large scale patterns. COVID in particular, starting in March and April, we've been asking a lot of dynamical modeling questions. How dangerous is COVID? How much should we be worried about it? When should we lock down? What are the prospects for COVID elimination, either without, in previous days, or now with an effective vaccine? What questions do we need to ask about these new vaccines in order to learn about prospects for COVID elimination? And how is control working? What policies are working to some extent? Can we get some idea of when policies are reaching people and when people are behaving as we hope for them to? Here's some time series from Canada that illustrates some of the difficulties. So in Ontario, where I am, not only has confirmations, that is to say the number of diagnosed cases of COVID, been going up in the last month or two, but so has the average positivity, the average rate of positives among COVID tests, which may imply that this rate, the actual rate of COVID infection, is going up faster than we think, because we may be doing less good a job of spreading our net. So those are the kind of questions we ask. I'm going to talk about foundational stuff because I think it might be interesting to a physics-based audience, and because it's the stuff that captures my attention the best. This is the part I took out most of these slides, in which I assume you're familiar with compartmental models. We make a simple dynamical model where we say people move from box S to box I under the influence of people move around in other autonomous ways. Once we have a conceptual model, we need to implement it, or we may need to implement it on a computer. It depends what questions we're asking. If we do that, the simplest way to do that is with ordinary differential equations, but there are many other ways to do it, including by treating individuals as individuals, or by taking, for example, discrete time steps, or both. Here's an example of what you get from this sort of simple model. And am I correct that this stuff, the last 2 minutes, is very familiar to the audience?
Yes, I think that's correct.
Yeah, go ahead. Yes, we're familiar.
So you may also be familiar with the fact that these systems interact strongly with stochastic processes. So that if I take this same simplest possible conceptual model, and instead of having people move perfectly smoothly, so that we go from one infected individual to 1.01 to 1.02 and so on, if I take a population of 100,000 with an average prevalence of 1,000 infected people, and I simply add demographic stochasticity, the smallest amount of stochasticity consistent with treating individuals as individuals, then I find that I was predicting the wrong slide. We get already a macroscopic amount of variation just due to the interaction between this small amount of stochasticity and the intrinsic dynamics of the disease. We can also take this simple model and add, for example, the realism of an exposed class, people who have an infection but are not yet infectious. And to match to data or to make predictions about something like COVID, people make much more detailed sorts of box models. I'm sure some of you have seen big nightmarish box models. This is one from Stanford that we used as a point of departure, where people split first into whether they're ever going to get COVID symptoms, clinical COVID symptoms, and then among those who do have clinical COVID symptoms, we split them again into those whose symptoms will be severe and will end up in the hospital, and those who have mild or moderate symptoms and will not. A thing that I like to use to bring together some of these different conceptual frameworks is what's called the renewal equation. And the renewal equation can unify a fairly wide range of deterministic models. What we do is we talk, instead of about the number of infectious individuals, we talk about the incidence of new infections, that's little I. And we say that the incidence of new infections depends on the incidence of infections in the past times some sort of kernel. If I got infected with COVID 2 days ago, or 6 days ago, or 10 days ago, on average, how infectious am I now? That's the kernel. And then we multiply that by the number of susceptible people, and probably I should have And in fact, this is normalized. This would normally represent the proportion of the population that's susceptible. And often if we're studying invasion or persistence, we imagine that this fraction is just 1. And here's all the things that I've talked through. So I'll take a couple of breaths so people can read through it in case my speaking is not super clear. But this...
Sorry, is that supposed to be the same little I on both sides of the equation?
Yes. Yes. So new infections now are caused by new infections in the past.
Oh, I see.
That's the conceptual framework. And that's what's illustrated here. Is it's the time from when I get infected to the time when I infect you. And the black line is an estimate, obviously smoothed, but a data-based estimate for Ebola of how infectious people might be a certain amount of time after themselves being infected. So immediately after infected, you're not very likely to be infectious. And here there's a peak, and we can decompose this kernel into a distribution with area 1 and a multiplier. And that multiplier is basically the reproductive number, is the number of new infections I would expect a given infectious individual to cause in a susceptible population. And we call the distribution that arises the generation interval, or the intrinsic generation interval distribution. And as you'll see, I've become obsessed in the last few years with generation interval distributions and other transmission interval distributions. So virtually any box model can be made fairly simply into a renewal equation model. You basically write and solve, or imagine that you've solved ODEs for what happens to a cohort of people infected at the same time. And you can do that for a simple model, and we have papers about how to do that analytically, which I'm not sure whether that's a good use of anybody's time, but they exist. And you can do it numerically for an arbitrarily complicated model. And if you're careful with your numerics, it works fine. You lose some information, or you make it harder in some cases to fit and figure out who's where. You certainly lose some information that might inform certain kinds of stochastic models, but conceptually speaking, it gives you a very strong framework to think about what factors go into how strongly and how fast a disease might spread through a population. So we're going to imagine taking a model like this and turning it into a kernel and asking what that tells us about the reproductive number and what that tells us about the rate of increase or decrease of the disease. So I'm obsessed with generation intervals, and I have lots of different ways of thinking about them. One way to think about it is, given that I get infected, how long until I become infectious, and then how long once I'm infectious until I infect someone else on average? What's the distribution of that? And I'm laying some stress on this because there's a very common error made of, especially by mathematicians and physicists, of conflating this infectious waiting time, how long on average until I infect someone, with the infectious period. And I see this mistake being made up until today, and it's not always a mistake for a reason I'll say, but it is always the enemy of clear thinking. The infectious waiting time does equal the infectious period, but only when we assume that the infectious period is Markovian and that infectiousness during the period is constant. And I like to think about it in terms of, there's a strong analogy between this and the bus paradox. So if we imagine that buses come on average every 10 minutes, right? So bus leaves the station on average every 10 minutes. All buses travel at an absolutely uniform speed. And I can ask how long I would expect to wait for a bus. And if you're a physicist, you would probably say that I would expect to wait on average 10 minutes for a bus. And that's a perfectly sound model. It's basically assuming that buses are Markovian, which here in Hamilton, Ontario, where I live, the buses do seem to be Markovian in the sense that you wait longer for a bus than you would expect to. The bus waiting paradox is, if the bus departure has no memory and buses leave the station every 10 minutes, then when I get to the bus stop, I expect to wait 10 minutes, fine. But it's also true that on average, it's been 10 minutes since the last bus. So if we assume that buses come every 10 minutes, then we can conclude that there's 20 minutes between buses. So that's the bus paradox. And the answer is that from the point of view of the average from the point of view of the bus and the average from the point of view of the passenger are not the same, because the passenger's experience is biased. I'm likely to arrive at the bus stop during a longer interval. And the math of this is exactly the same as the math of the relationship between the infectious period and the infection waiting time in a simple model. And it's a lot of fun. That's sort of a digression. It's, I hope, was well designed to catch the attention of some of the more math-oriented people in the audience. But basically, if we assume that infectiousness is constant over the infectious period, then we get a self-weighted mean of infectious periods for the infectious waiting time. There's a very similar piece of math you do in many other contexts in population biology. An important one is if we're doing sexual or other mixing models, where my tendency to meet people and maybe get infected is proportional to my tendency to meet people and maybe infect others. We get these activity weighted means, and it's very cool, and it all comes out perfectly in the case of the exponential distribution. So we have this idea of a generation period and a kernel, and I'm working on developing a conceptual framework of thinking about strength and speed of epidemics and from a mathematical or a conceptual point of view. So what we learn from simple models is that diseases have the potential to spread exponentially at first if we don't do anything about it. That diseases have a tendency to oscillate. I didn't talk through that for this audience, but I assume you're familiar with it. And then there's this idea of thresholds based on big R. And I'm going to try to introduce some new vocabulary. I've had some pushback, but I'm going to refer to big R as the strength of an epidemic. If I get sick, on average, how many people do I infect? The number of new cases per case. And we can think about R with lots of different qualifiers. And in particular, R naught was the famous one up until COVID. Now R sub T has become very famous. R sub T is not exactly well defined. But the history of big R goes back over 100 years to Ronald Ross, who argued that if you take a generational perspective, you're going to make different predictions about the long-term behavior of infectious disease. And in particular, he argued that you can break cycles of transmission without ever knocking out one of the pegs. So that if we do mosquito control, even if we still have plenty of competent mosquitoes who are occasionally biting people and have the ability to pass malaria, if the average number of new cases per case is less than 1, then malaria is going to go absent from an area more or less naturally. And that has proved to be a really powerful insight. So here's the relationship. If we have reason to believe that I forget now what word I use for V. Doesn't matter. That the proportion of a population effectively affected by disease is around here, then we would say, well, if we can remove 60 or 80% of the mosquitoes from contact with people, we don't expect to just reduce disease incidence by 60 or 80%. We expect to reduce disease incidence all the way to 0. And that insight has given capital R a very strong role in the way people think conceptually about infectious disease. And if I have time, I'm going to argue that maybe we've swung too far towards capital R. So I guess people are roughly familiar with all this. That's the curve that I just showed you. So in addition to using the word strength to talk about big R, I'm going to use the word speed to talk about little r, and that's literally just the speed at which a disease passes through a population exponentially. So we're going to call little r the speed, has units unlike big R, and we're going to say the disease increases exponentially at that rate. I may sometimes talk about the characteristic time scale, which is 1 over the rate, because we're all mathematicians and we think doubling times are a little awkward. And sometimes we can observe little r quite clearly for a disease. So here's data from South Africa, specifically about the early spread of HIV, and it looked quite exponential, and we can get a pretty narrow estimate on the rate of exponential growth. The same was true when Ebola was first spreading in West Africa. We didn't know what the strength was, but we knew what the speed was. And the same was and may still be true for coronavirus. I also put the characteristic times here. The characteristic times are interesting because by themselves, they don't tell us everything we need to know, right? The 18-month characteristic time for HIV is actually quite fast because nothing in physics is big or small until you compare it to something with the same units. And HIV is a very slow disease inside of individuals. So for coronavirus and some of these other diseases, what we see clearly is little r. And for coronavirus, more than anything else, in the early months, there was just this stampede to calculate big R. Often people, even though all the calculations of big R were indirectly based on information that pointed very clearly at little r, people didn't even talk about little r. Modelers didn't. They were just in such a rush to calculate big R. So I'm going to talk about how we calculate big R from little r and try to get an intuition for what links them, which is generation intervals. And I'm also going to talk about why we do it and argue that maybe we're a little bit too affected by history and that we should be treating speed and strength of the epidemic in a more balanced way. So back to my friend, the generation intervals. And this is an illustration made by my friend David Champredon. This person got sick on day 3, and this person is still going to get sick from this person on day 8. So that's a generation interval of 5 days. And generation intervals, in my experience, are things that modelers treat as annoyances. You try to find enough data that you think your generation interval isn't too unrealistic, and then you get back to the more interesting business of worrying about little r or big R or bifurcations or whatever you're worried about. And we've used very ad hoc methods for generation intervals. The early estimates of big R propagated error from their incidence estimates, but mostly not from their generation interval estimates. So I'm going to introduce a third word that I'm hoping to use to spur you into action, which is quickness. So I've talked about the strength of the epidemic, the speed of the epidemic. Quickness is, speed is how quickly, in my lexicon, speed is how quickly the disease is moving through the population. Quickness is how quickly it moves through an individual. So I use it for the generation interval distribution or for the mean of the generation interval distribution. Here is another manifestation of the fit that we made to the Ebola data. So again, it's saying that if you have Ebola, on average, you don't infect very many people in the first few days, and then your capability of infecting people goes up and then back down again. And it's the generation interval that links little r and big R. If I knew the generation interval and I knew big R, then I would be able to tell you how fast a disease would spread through a population, and conversely. So we could ask, and we did ask in the case of Ebola, are short generations, if the disease is quick at the individual level, is that good news or is it bad news? And here's a picture of a famous robot who's very worried about danger, and it's just meant to get me to slow down and hopefully to get you to think about the question, if the disease is quick, if it's fast at the individual level, is that good news or bad news? And the answer is, it depends on what else you know, right? Most of us have the intuition that quick disease is bad news, and that's a perfectly valid intuition. In particular, if I already know the reproductive number, if I already know the average number of new cases per case, then the quicker the disease, the faster the growth rate and more danger. But often that's not what we know. If we were thinking about HIV in sub-Saharan Africa in the 1990s, it's the opposite. If what we know is the growth rate little r, then as a corollary of this paragraph, we have this paragraph. If there's a quicker disease and we don't know big R, then the faster the disease we have, the less spread at the individual level we need in order to explain the little r that we see. So this is really, to me, an important insight. I'm certainly not the first person who had it, and I'm not even sure that I did have it. I might have stolen it from somebody else subconsciously. And it's been very much in the literature, certainly the HIV literature, to the point where I can find nice pictures of it and I don't have to make one. So here we've imagined that little r, they've imagined that little r is known. So both of these diseases have spread in a way that they multiply by a factor of 16 in a fixed time unit. If we learn that our disease generations are short, what that means is that each individual is spreading to many people. And if we learn, and when I say short, I mean long. If we learn that our disease generations are long, each individual has to spread to many people to reach 16. Whereas if we found that the generation intervals are shorter, we don't need as large of a big R. And this was a very relevant question for Ebola, where people were making very complicated models about the importance of late transmission of Ebola. In fact, people who were transmitting Ebola after they were dead. And what was emerging from some of the models, but not realized as a basic principle, was that because we knew the rate of exponential growth, the more late transmission you have, the higher value we would infer for R naught. That this quicker epidemic would be bad news. So this is simple but confusing, so I'll step through it one more way. I like to think about the speed that a disease spreads through a population as a product. The more strength there is, the more a single individual can spread, and the quicker it is, the faster that individual has their own course of infection, the faster the disease at the population level. So if this is a product, then going in the other direction, getting big R from little r, is a quotient. We're dividing by something to do with quickness to get something to do with strength. And importantly, sometimes we observe speed in a population and we want to use the generation interval to infer the strength. Other times, if a disease has been endemic for a long time and conditions are changing, it may be easier to infer big R, the speed. So how do we link these two quantities? Is with the Euler equation. Many of you will be familiar with this. It's very simple math. But if you know the kernel, you can find little r. And that gives us this relationship. If we factor the kernel into a distribution, and the multiplier, which is the strength. And I'll note that G of t is a distribution, but this is also a distribution. And we'll come back to that. And the typical way that people link big R with little r is via a paper from about 10 years ago, where they pointed out that this can be done with generating functions, which I've always found confusing. It's useful and people get right answers with it, but it's moving sort of in the opposite direction of an intuition. And what I've tried to do is think about, with collaborators, is think about big R as being a generalized exponential of the product of the mean generation interval and little r, the rate of growth. And the generalized exponential, this is sort of like the compound interest formula, that as the exponent gets larger, this approaches the real exponential. When the exponent is 1, this reduces to a linear formula that some of you will recognize. And what controls the exponent is the effective dispersion, how broad the generation interval is. And there's an intuition for that as well. So first of all, why does big R get bigger when this product gets larger? Well, this product gets larger when the disease is spreading more slowly. And when the disease is spreading more slowly at the, when the disease is spreading more slowly at the individual level, we require a bigger capital R to get to the same little r. Similarly, if our generation interval distribution is broad, then we have people infecting people who infect people who infect people quickly. The broader the generation interval, the more extra compounding we get compared to the mean speed. So a narrow generation interval also makes it harder for the disease to spread, and therefore also means we require a larger strength to achieve an observed speed. Okay, since I'm struggling to understand this at this speed, I'm assuming that others are as well. I think what I'll do is go forward. Some version of these slides is publicly available, but I'll make sure to update that. And of course, I'll be available for questions as well. So these approximations work. This is an example we did for Ebola. The lower black line is what you would get from an ordinary differential equation model. The upper black line is what you would get from the from a model with fixed generations, where we don't allow any variation in the generation interval. So it's basically a discrete time model where the time step is generations. The black line is what we got from a detailed model of the observed Ebola kernel. And the black points are what the WHO got from a slightly different detailed model of Ebola. And sorry, that's probably the blue line that's our model. And the black line in the middle is what you get for the predicted relationship between big R and little r given a fitted value of the dispersion. In other words, we can do a good job of estimating big R if we know the generation interval and a single shape parameter, but not if we know only the generation interval. And we showed more or less as a proof of concept because we analyzed data up through early March, I think, but didn't get the paper out until June. COVID has really been crazy, but we took some of the early studies of COVID and we asked, basically, we boiled down however they estimated big R to the simple steps that correspond to using the generation interval to get from little r to big R. And we asked what happens if you include uncertainty just in the incidence rate, just in the rate of growth, or if you include all forms of uncertainty. And we did it with the baseline, and we did it also going forward in the counterfactual of more data. And what we show is that you can propagate the two kinds of error, the three kinds of error that are the main source of uncertainty for big R estimates during exponential growth, which are uncertainty in little r, uncertainty in the mean generation interval, and uncertainty in the effective dispersion in the time it takes to pass disease from one person to another. So when I started looking at generation intervals, stopped treating them as the poor relations, every disease modeling question I look at now looks to me like a transmission interval question. They're fascinating, and they're extremely hard. We have all these simplistic arguments for why you can look at a generation interval or a serial interval and just use it, but you really can't. And one useful way to frame it is to think about how do we try to estimate generation intervals. There's two main ways. One is by observing individuals, often in challenge trials. So we get healthy volunteers and we give them flu and we study them. How long does it take to become infectious? How long does it take to recover? What are the profiles of viral shedding across that time? The more common way, of course, is to try to figure out who infected whom and when. And of course, when is the hard part of that. But who infected whom, when, and when did they become infected? And if you can't tell when they became infected, you try to tell when they became ill. And that turns out to open up a whole other can of worms, which I'll get to later. The first can of worms, which was discovered in part by theorists, is that we expect the generation interval to be a fixed quantity given to us by the kernel. But even in very, very simple models, it doesn't come out that way. Even if you do a simple model, the realized generation intervals seem to change through time and, of course, differ from these intrinsic estimates, which in the simple models do not change through time. And so most of this work was done earlier in various forms, but we tried to get everything together and make clear definitions of first the intrinsic interval. How infectious would I be, assuming that nothing about the world is changing around me? We defined a forward interval, saying if we take a group of people infected today, on average, when will they infect others? And a backward interval. Of the people infected today, when were their infectors infected? And the backward interval, well, the forward interval is particularly relevant to the dynamics and to the RR link. And the backward interval is particularly relevant to the data, right? You're scrambling to get as much data as you can, and you don't see what happens to the people. You don't see who the people infected today will infect because it's today and you can't see tomorrow in your data set, typically. And what we found is that backward generation intervals in particular look shorter at the beginning of the epidemic, and this should make perfect sense. If you, the actual generation interval for HIV is still problematic, but if we imagine that somebody infected in 2005, maybe if we look backward, their infector might have been infected 5 or 6 or 7 years ago on average. That's literally not possible in 1995. If we go back 3 years, almost nobody was infected. And that's going to cause a very strong bias. The people infected in 1995 were mostly infected by people who were infected only 2 or 3 years before that because of dynamical reasons, not because of the intrinsic generation interval. And we showed that basically it's changes in the pool of people who might infect you that are the main biases in the backward generation interval. And it's changes in the pool of people who might infect that are the main source of bias in the forward generation interval. And we showed that with this in mind, we could do simple simulations and get just exactly the right answer for how we expect these intervals to change through time dynamically. We also looked into some work done by Peter Trapman and others about how generation intervals were affected by space. And the basic answer is that if the population has spatial structure, that tends to shorten generation intervals more than you would expect from non-spatial things, because I'm interacting with the same people over and over again. And if I've infected you yesterday, I can't infect you today, even if a homogeneous model thinks that I would, because you're already infected. I'm looking at my watch and I want to go through this a little bit quickly. Spatial network structure shortens generation intervals, which therefore leads to smaller estimates of capital R, but those smaller estimates aren't necessarily wrong. What we really want is the effective generation interval, which is more or less the realized forward generation interval. And what we're observing so this is a complicated slide. I need to slow down a little. If we're observing using contact tracing, what we're observing is the realized backward interval. And so we don't need to worry about the spatial correction. The spatial correction is already built into what we observe. We can do, or we expect to be able to do, a temporal correction, like the backwards intervals I showed you, and get the right answer. If we're doing a patient-based study instead of a contact tracing-based study, then we do need to worry about the spatial correction, and the spatial correction is hard. We can do a local spatial correction, but to do the full network spatial correction is basically the whole problem of networks and percolation, and we haven't tried it yet. But we did do simple simulations, and we showed that for the same spatial epidemic, if we do a naive contact tracing study, we sharply underestimate R0, but that we can do a temporal correction and get an unbiased answer, and with a lot more work, get a stable and unbiased answer. If we instead look at the intrinsic generation interval, remember this is a simulation study, so we can get the intrinsic generation interval more or less exactly right. The uncertainty here comes from the difference in the realized rates of spread, and we can do a simple spatial correction, which takes us about half the way to the right answer. So I know it's a lot, but the take-home lesson is that there's a lot of different generation intervals that you can define and measure, and that it can matter, right? In this simple study, we have the ability, if we're naive enough, to estimate R0 anywhere from 3 to 6. Trying to figure out, so that's a log scale. So it's 3 to 5.5. It's very confusing. Like, it's very hard to look at this and not think it says 2, 3, 4, but it doesn't. Serial intervals have become very popular since COVID. And what's a serial interval? A serial interval, I said too fast before, so I'll say it slowly now. If the generation interval, if I get you sick, the generation interval is the time when I get infected until the time that I infect you. The serial interval is the time from when I show symptoms until the time when you show symptoms. The generation interval and serial intervals describe generations of the same process. So it seems like they should be the same. Seems like they should have the same distribution. It certainly seems like they should have the same mean. People are routinely using serial intervals as proxies for generation intervals, and it turns out to be a can of worms. It's been long recognized that the distributions are not expected to be the same in general. And when infectiousness is disentangled from symptoms, this becomes obvious. So that, for example, in influenza, it's routine to see negative serial intervals, and there's no real problem with that. I might get the flu, I might barely have a sniffle, I might think I'm fine, I might infect you, you might show up at the doctor 2 days later, I might show up at the doctor 2 days after that, right? So now the generation interval is positive 2 days, and the serial interval is negative 2 days. A generation interval cannot be negative, right? There's no way that I can infect you before I become infected, but you can show up at the doctor before I do. And if we're talking about COVID tests and reporting, it becomes even more clear that that the distributions can be different. We still expect the mean to be the same, and we're still wrong for a number of reasons. For rabies, I've been arguing publicly for years that the distributions should be the same because you can't infect somebody with rabies without showing very identifiable symptoms. And so the rabies serial interval and the rabies generation interval are simple sums, and they're sums of the same three kinds of things. An incubation time, the time it takes for me to become symptomatic, an extra latent time, which some people ignore, the time that it takes for me to become infectious, and the waiting time, the time it takes me to infect you. Similarly, the serial interval is my extra waiting time, latent time, plus my waiting time, plus your incubation time. So I've been saying this for years, and finally had Mike Lee, who did this as he was transiting from being a grad student to a postdoc, actually observe the world's best data set for rabies generation and serial intervals from Tanzania, and find that they are sharply different. The generation interval is far longer than the serial interval, and the reason is because of individual level heterogeneity. A generation interval always has an incubation period from a biter, from somebody who successfully transmits the disease. And in fact, the more times I transmit the disease, the more time my generation interval gets counted. Whereas a serial interval gets its incubation periods equally from everyone. And that turns out to be enough in basically the best real world case study that I know of to make a huge difference. So serial intervals aren't the same as generation intervals in real life if individuals are heterogeneous. So that was a blow. Shortly after I learned that and sort of incorporated it, we also learned that they're not even the same if individuals are assumed to be homogeneous. And in fact, they can't be the same even when individuals are assumed to be homogeneous. And the way we see that is to go back to generation intervals as the link between R and R. There's no logical reason why we can't say that serial interval is the link between little r and big R, right? I mean, we know that physically that's not what happens, but we could imagine a process that works somehow through symptoms and produces the same result we saw, and we would expect it, therefore, to produce the same link between little r and big R, but we know it can't, because we know that in general, serial intervals are broader than generation intervals, and we know that broader intervals in general lead to flatter links between little r and big R. And the resolution of this paradox is fascinating to me, which is that serial intervals, even at the beginning of an epidemic, when the number of susceptible individuals isn't changing, dynamical effects can shorten the forward serial interval. And they do this because the mechanistic way of constructing a forward serial interval is we start at the time when I develop symptoms. We need to go backward in time to ask when I was infected, and then forward in time to ask when I infect you, and forward again to ask when you develop symptoms. But this backward incubation period, given that I show my symptoms on a given day, there's going to be a bias here when the disease is increasing rapidly. If the disease is increasing rapidly, I'm likely to have a shorter backward incubation period because I'm likely to have become infected more recently because everybody was likely to have become infected more recently. So I am out of time and I still have about 1 billion slides left to go. Here's an illustration that we verified this effect with COVID-like parameters, and it really all works. I promised to give you a rant about how strength is overrated with respect to speed and speed underrated with respect to strength, and I think I shouldn't do that. And then I was also going to talk a little bit about the strength and speed perspectives on figuring out how we're doing with COVID and just the general difficulty. I mean, some of you will have seen this debate about how quickly the control measures in Wuhan were effective, and it's all about hard mathy questions of interpretation, of taking data and pulling out time delays in some cases with deconvolution. Okay, well, I gave 3/5 of my talk, but I'm a believer in finishing. So I am going to apologize for talking slowly or for trying to say too much, whichever you prefer, I apologize for, and thank you for your attention.
Thank you very much, Jonathan, for this actually very interesting seminar. And there is no need to apologize, actually. So, colleagues, do you have, if any of you have any questions for Jonathan, just simply switch on your microphone and go ahead, please, or just write something on the chat and I'll read it.
Hi, Isaac. May I ask a question, please?
Please, yes, well, Nancy, go ahead.
Okay, thanks. Hi, Jonathan. Thanks for your presentation. And just I have 2 questions. So, well, I had 3, but now at the end you mentioned actually the answer for the third one. But the first one is, can you repeat or can you, yes, kind of explain again what could be the effect of individual heterogeneity in, I mean, does this have a greater influence in generation or serial interval, in which of both?
So what we found, right. So what in the rabies case, I'm not sure I know the answer to the general question, but I definitely know the answer to the specific question. I'm going to switch. I have a slide deck that only has 1 page per page. I'm going to try to do that because I'm making myself crazy now. I guess I could have used the search. I didn't think of that. Okay. Here's the good slide deck, and maybe I'll use the search as well. So we're looking for hetero. Huh. I think the word heterogeneity would appear in this document, wouldn't you? Okay, how about the word rabies?
Yeah, okay.
Okay, good, that was better. So in the rabies case, It's the generation interval that's strongly affected by heterogeneity, because there's a correlation between how long, a positive correlation, surprisingly to me, between how long my incubation period is and how much I bite. And so the generation interval is the serial interval is a good match to the incubation period in the population, plus for rabies, a very small latent and waiting period. But the generation interval doesn't match the population level characteristics. It matches the bite weighted characteristics. So actually there's an analogy there with the bus problem as well. Right? It's a weighted mean instead of a simple mean.
And well, in terms of how do people realize that the COVID and other diseases maybe people start infecting other people before showing symptoms, using generation intervals or serial intervals, or how do they get to know this information?
Right. So serial intervals and generation intervals for COVID are almost entirely determined through contact tracing, trying to figure out who infected whom. And that's also roughly the main source. It's the contact tracing itself that's the main source of information about whether I infected you before I became symptomatic or after, or whether I ever became symptomatic, right? So the thing people are looking for with the most fear are people who have COVID but didn't meet anybody with COVID symptoms, right? So that's strong evidence of asymptomatic. And then beyond that, and I don't know if you followed in the beginning, people were overexcited, and there was this one case of a person who their acquaintances reported that the person didn't have symptoms, and it was a paper in Lancet, but then some other authors reached the person themselves and they said, yeah, I had symptoms. I was just, covering them up for something. I had no idea it was COVID.
Okay, thanks. And well, if there is no one else, I actually have another question, but I might wait.
Please, Nancy, go ahead.
Okay, and does they mean, or how to take into account that these generation intervals or serial intervals or the intervals that you mentioned can change over time? Would that happen? And if that happened, how to include this information in a model? Or
so it absolutely happens, and that's sort of what we're most worried about right now. And right at the very end, the thing that we've realized, so first of all, I skipped a whole part of the talk about sometimes what you want to look at is strength, and that's the classic paradigm, but that there's an equally good paradigm that involves looking at speed. And instead of comparing big R to how strong an intervention there is, there's a consistent way for comparing little r to how fast an intervention is. And the speed is based on sort of hazard, the idea that I isolate people at a constant rate once they become infected. So that's all cool. Coming back to your question, yes, generation interval distribution can change, and that's mostly ignored. These classic paradigms ignore it. And what we've been finding is that you can't tell from incidence data what's changing. So a speed-like change where it's big R that's changing cannot be told just from incidence data from, speed-like change where it's just the removal rate that's changing cannot be distinguished. I can give you identical incidence curve. And so then it comes down, which one we should be assuming comes down to what changes we're making. If we're vaccinating people, then we probably want to assume that the generation interval is staying constant and that it's the proportion effectively susceptible that's changing. You know, or if you have a lockdown, that's more of a strength-like intervention. If we're doing testing and treatment, or if people are isolating themselves based on suspicion or symptoms, that might be more of a speed-like intervention. And in that case, we might want to assume the generation interval is changing. And in that case, we might want to be using measures of speed instead of measures of strength, the instantaneous measures of speed versus strength. So thank you. If I had planned to get that far behind and planned for one question that would enable me to hit that one point, that would have been the question.
Okay, thanks.
Thank you very much, Nancy, and thanks, Jonathan. Colleagues, more questions? Do we have time for a couple of more questions, if there are any?
Yes, please.
Adan, go ahead.
Yeah, thank you. Thank you, Professor, for the conference. There is an issue with symptoms that is on clinical medicine, defining a symptomatic period. It makes a lot of blurry sets. Yeah, you know, even between doctors can't always agree on what is a symptomatic patient. I will say there is operational definition in these cases, but they say that patients not always read that operational definition, you know. There are some articles that support that transmission might start even to 2 days before symptoms, and the viremic peak also matches on that time period. That was a commentary, but I have a question. You said that the effectivity for transmission plays a role, and I want to ask how to match this measure that we call secondary attack rate with the generations, the capital R and the little r. Please. Thank you.
Okay, there was a lot there. I guess the first part was not meant to be a question, but I sort of want to take it as a question. The second part is hard for me. Let's start at the end. So I haven't thought much about secondary attack rate at all, and it's confusing. I mean, all of your questions come down really to how hard things are to measure, right? So secondary attack rate means how many of my contacts do I infect? When did I contact them and for how long? You know, there might be one contact who I saw every day from the day I was infected until the day I got better, and I infected them. That's 1 out of 1. There might be somebody else who I saw just on day 2, and I didn't infect them. Somebody else I saw just on day 7. So these questions are all hard, and they're all filtered through the difficulty of observation. What we actually observe is patients tell us, according to different questionnaires, roughly when they achieved some symptomatic status. Some people never do, right? And so do these people have serial intervals or not? I've tried in my mind to talk more about transmission intervals. So what transmission interval is an interval between some reported date or some inferred date of me and some inferred date of you who I infected. Hopefully these dates are analogous to each other. But, oh, and the other issue I wanted to touch on is just the whole idea of asymptomatic and symptomatic infection as a binary, I don't really like. And based on my own experience, I feel like my immune system has a huge spectrum of statuses. And there are many times that I've been convinced that I was fighting a viral infection, but I never got anything like sick. So I like to think about the spectrum. I like the word subclinical. It depends on the disease. But for Ebola, certainly there were people who transmitted Ebola, not very many, without ever having clinical Ebola disease, but I don't think those people were asymptomatic. So there's the question of the spectrum of viral effects. There's the question of how that maps onto what we can measure about infections. And I had a slide about that too that was mostly meant to admit that it's hard, right? What dates are we thinking about? And what dates are we observing? And what are the relationships between those dates? I hadn't thought about it in terms of secondary attack rate in particular, but if I were to start thinking about secondary attack rate, those would very much be the questions in my mind. When did I see you? And there are models like that that try to say, well, this person saw that person from day 3 to day 6, but then there's also the questions of how to average over courses of infection, right? We know, or we may think we know what the average course of infection is, but to do the secondary attack rate right, we would also want to know what the correlations of infectiousness pattern are within an individual. I'm sorry, I know I said a lot, and these are all things that you made me want to say. I don't know if I addressed your question satisfactorily.
Thank you, doctor. You got me perfect. Thank you.
Thank you, Alan, for the question. One last question, if anybody has one. Not? Okay. So then, so Jonathan, thank you very much for this fantastic talk. So shall we upload? Shall we unmute the microphones and upload Jonathan for this fantastic talk? People, thank you very much, Jonathan.
You're very kind. Thank you again for the invitation.
Very good, guys. Thank you very much, Jonathan. A pleasure to have you with us. See you next time. Okay, perhaps you know, personally in Mexico.
I hope
Bye-bye.
so. Yeah, I feel like you owe me a meal now.
Yeah. Thank you very much. Take care. Bye bye.
Gracias.
Gracias a todos. Hasta luego.